All right, so we have stroke number 1, which is an isobaric expansion. So this has W12 equal to P1 V2 minus V1, and Q12 is equal to gamma over gamma minus 1 P1 V2 minus V1. Okay, so this is the first. The second adiabatic expansion. Adiabatic has V12 equal to, all right, so here I write n times r divided by gamma minus 1. I go by the definition, T3 minus T2. But then, you know, at the end of the day, I want to write everything in terms of pressures. So I use the equation of state, and I rewrite everything in terms of what I called here P3. Some of you called it P2, but I prefer to stick to P3. So P3 V3 minus P1 V2 divided by gamma minus 1. Okay? Then, sorry, I have to be careful here. This is an expansion, so therefore the 1, 2, 3. I think I got a wrong minus sign. 3 and 4. I think it's the other way around. Why is it the other way around? Why is it the other way around? Just a second. Now I am getting confused myself, right? So, I mean, as it should be. No, I think it was correct. So my calculations there are wrong. Yeah, is it correct if I put the signs like this? So let's see. P3 V3 minus P1 V2. Does it agree with you?
Yeah, because the volume is increasing.
The volume is increasing, so it's work done by the gas on the external thing. So it's okay. I think it's correct at the end of the day. Good. So therefore I have some wrong. Oh, what did I do? I erased. Good. Now 3. Well, 3 is again an isobar, so I have W34 equal to P3 V4 minus V3, and then Q34 equal to gamma over gamma minus 1 P3 V4 minus V3, and then finally I have number 4, which is W41 equal to, following the same reasoning as before, should be equal to, in this case, P1 V1 minus P3 V4 divided by gamma minus 1. Correct?
Yeah.
Good. All right, so now, what is W? W is equal to P1 V2 minus V1. So this is the first one. Plus P3 V4 minus V3. So this is the second isobar, plus, and then here I have to be careful, plus P3 B3 minus P1 B2 divided by gamma minus 1 plus P1 V1 minus P3 V4 divided by gamma minus 1. Okay? Good. Now I use the equations. I want to simplify this. So I start using those equations that tell me that on the adiabatic P3 V3 to the power gamma is equal to P1 V2 to the power gamma. And at the same time P3 V4 to the power gamma is equal to P1 V1 to the power gamma. Okay? And therefore this tells me that P3 over P1, sorry, let's write it like this. This tells me that V1 over V4 is equal to V2 over V3, which is equal to P3 over P1 to the power 1 over gamma. Okay? Great. So now what I do is I take out of this P1 V2, right? So I collect everywhere here P1 V2. And therefore what I get is P1.
What's the motivation for collecting P1 V2?
The motivation for collecting P1 V2 is the following: that when I look at what is the heat that is put in the system. Okay, I didn't explain this. Let's do it slowly. So, what is the heat? What is the heat that is being exchanged with the system? The total heat, so this is the total work, and the total heat is this, okay? So this is the total work, and this is the total heat, okay? So now, in the total heat, I can collect P1 V2, right? And you see that I get the total heat Q12 equal to P1 V2 divided by gamma minus 1 times gamma times 1 minus V1 over V2. But what is V1 over V2? V1 over V2 is P3 over P1 to the power 1 over gamma. So this is gamma over gamma minus 1, P1 over V2 times 1 minus P3 over P1 to the power 1 over gamma. Alright? So now if I collect in the other expression P1 V2, since the two are one on the other, I will simplify and get everything. Okay? So let's try to do it. So I have, let me do it using modern technology. Copy. Put it here, paste. So I collect P1 V1, so I get P1 V2 1 minus V1 over V2. Then here I have P1 times P3 over P1. And then I have V2, just a second, V4 over V1. So, and then I have V2, and then I have V4 over V2 minus V3 over V2, plus, etc., same thing for the others, okay? And then you see that here, for example, V4 over V2, this thing here, I have to re-express it as V4 over V3. So here I have V2 over V3, V1 over V4. So I can rewrite it as V4 over V1, V1 over V3, and then use the, I'm getting completely messed up. How did I manage to do this? Just a second, guys. V4 over V1. Okay, so I'm the guy who's not even understanding his own notes. Here I see it. Okay, here is written. So, sorry. If, for example, you try to rewrite here P3 V4 minus yes, which is this one. Okay, I'm not understanding my notes, guys. I'm completely messed up with my notation. So I apologize. So you see that your calculations were complicated and also mine. I thought it was much simpler, but apparently is not. Anyway, what I have to do is rewrite everything in terms of P1 V2, then 1 minus P1 over V2, then plus P3 P3 P4 now I understand what I've done. No, I'm sorry, guys. I've been an idiot up to now. Okay, sorry. I apologize. I'm not collecting P1, V2, of course. Otherwise, I'm not able to do anything. Okay. So what I've been doing is I've been rewriting this term here and this term here separately, using those relations for the adiabatic. So in particular, W23, once you write down everything for this adiabatic, comes out to be P1, P2 divided by gamma minus 1 times 1 minus P3 over P1. So here I'm collecting on the first one P1, V2 to the power gamma minus 1 over gamma. The second one, W34, I collect not P1, V2, but I collect P1, V1. So I can get out P1, V1 divided by gamma minus 1 times 1 minus times P3 over P1 to the power gamma minus 1 over gamma minus 1. And now, when I put them together, you see that they come out to be W23 plus W34 equal to P1 V2 minus V1 divided by gamma minus 1 times 1 minus P3 over P1 to the power gamma minus 1 over gamma.
So, I know the step right that I have before this.
The one above here.
Yes.
So here you just take this expression here, collect P1 V1, and
okay.
re-express everything in terms of the ratio V4 over V1 and P3 over P1.
Okay.
Okay?
Okay.
In this one, I collect instead P1 V2, and then re-expressed everything in terms of that ratio, of those ratios, the ratios that are written up here. Now, if you do this calculation, then this is what comes out. And everything is expressed, I'm sorry because I said something incorrect before, is expressed in terms of P1, V2 minus V1. Now, why did I do this? Because I can do the same also for these two terms, because I know what is the ratio of V4 to V1, and I know what is the ratio of V3 to V2, okay? And I can re-express them in terms of this. And moreover, I know also that the heat is written up in terms of P1 V2 minus V1, okay? And therefore, when I take now the ratio of the sum of those four terms, V1, 2 plus V2, 3 plus V3, 4 plus V4, 1, to the heat in the first stroke, then I get that the P1 V2 minus V1 cancels. Okay, and the only thing I'm left with is gamma over gamma minus 1. Sorry, it's not gamma over gamma minus 1. Is according to, well, I'm skipping a bit of calculations here. 1 P3 minus P1 times gamma minus 1 over gamma. So this should be the final result. But since I've been making a mess of signs in this derivation here, the derivation was correct. I mean, I get the P1 V2 minus V1. But I've been making a mess of signs, as I noticed. Please check it, because there might be some problem. At the end of the day, you will get an expression of this type. What did you get?
That expression was 1 over gamma.
Times 1 over gamma. That is weird, because you know, you should have an efficiency that in some limit, well,
It should tend to 1, not to 1
it should
over gamma.
tend to 1, not to 1 over gamma, so it's quite weird. I think, but maybe it's correct.
No way.
Check it. All right? This is not the simplest cycle in the universe, okay? It's not even like the diesel cycle. But in any case, I mean, these are the kind of calculations that you will be finding in all standard cycles that you find in exercise books and things of this type. All right, so we have 15 minutes now, because I've been messing up the calculations myself. So let us now do one thing, which is define the entropy, and then we will continue next time. Now, today we are going to define the entropy according to its definition in thermodynamics, not in information theory. Now, the definition in thermodynamics is something quite mysterious, okay? At least in my perspective. But But what is interesting is that the connection between what we have done in information theory and what we're going to do today in thermodynamics is going to come through this Boltzmann formula, which we're going to write down in the first lecture on statistical mechanics. The famous formula that is entropy equals, entropy not a circle, entropy equal to K Boltzmann log of, I don't know. So this is a super important formula, we'll see it. So how do you define entropy? Well, the idea is the following. We know that for each cycle, for each engine, the efficiency is always smaller or equal than the Carnot efficiency. Okay? And this in particular, if it falls, then it's irreversible. So the entropy grows. And it's not, unfortunately, you don't get zero entropy when a cell phone falls. All right. Anyway, so this means that Q1 over Q2 should be greater or equal than T1 over T2 in order for this inequality to be satisfied. Or in other words, that Q1 over T1 should be greater or equal than Q2 over T2. All right, so now remember that this is the heat that is gone to the environment, to the reservoir, and this is the heat that is taken by the reservoir. Now, if we always count the heat in the same way, so the heat that goes out of the system has positive sign, that the heat that comes in the system has negative sign, then, so if we always count the heat, for example, as being absorbed by the environment, then we just have to change sign to Q1. Q1 goes to minus Q1. Okay? And then this means that Q1 over T1 plus Q2 over T2, if you take this equation, make this change of sign. So if you do this, and then this, then this one comes out to be smaller or equal to 0. Okay? So heat absorbed by the environment, the heat that goes out of our system. Now, this is true for one engine, but we can think about putting a sequence of engines in a chain, each one exchanging minimal amounts of heat with the environment, and therefore we will have in that case that sum over I, Qi, Ti should be smaller or equal to 0 in general, okay, for this sequence of engines. And in practice, if you now take an infinite sequence of engines, each one doing very little, okay, then you will get that this quantity, the integral over a big cycle, which is just this sequence of engine, of dq over t, should be smaller or equal to 0. Okay? So this is a theorem. There's nothing to say about this. You can, if probably there are some mathematicians who try to prove this using epsilons and deltas and some Hilbert or Banach or whatever space structure, but it's a simple fact of life. Now, when is the equality satisfied? The equality is satisfied, if you look where it comes from, the equality is going to be satisfied when?
When the process is adiabatic.
When the process is not a self-unfolding, but is a reversible process. A reversible process. Because the Carnot theorem tells us that the efficiency is maximal for any reversible thermal engine operating between two given temperatures and is given by 1 minus T1 over T2. So this is going to be, the equality is going to be for reversible. For reversible engines, you're going to get an equality. But now let us think for a second. The fact that you have an equality for reversible engines means, mathematically means something deep. Means that you can define, using this integral, an equation, a state function. Why? Well, it's very simple. If I have some function, and I know that my integral over a cycle is equal to 0, is always equal to 0, if I move, of course, reversibly over this cycle, then I can do the following. I can split the cycle into two pieces that goes from A to B and write my cycle as integral over the cycle of dq over t. I can write it as the integral from A to B dq over t plus the integral from B to A of dq over t. But the integral from B to A is minus the integral from A to B. But is the integral, sorry, we have to be precise here, otherwise we mess up. This is the integral from A to B going along, I don't know, this path, let's call it gamma 1. And this is the integral from B to A going along the path, let's call it gamma 2. Okay? So this is going to be equal to the integral from A to B over gamma 1 dq over t minus the integral from A to B over gamma 2 dq over t. Okay? And therefore, the fact that this is equal to 0, because we are dealing with reversible transformations, implies that this integral for a reversible transformations does not depend on the path I'm taking to go from A to B. Okay? This is the consequence of our Carnot theorem and of all this other theorem that I don't remember to whom belongs, maybe Clausius, maybe someone else, I don't remember. And that's it. But now if I have a function, if I have an integral that does not depend, in order to go from A to B, does not depend on the way I go from A to B, then I can use this integral to define a state function. How do I do that? What is a state function? It's a function whose value depends only on the point in parameter space. Does not depend on how I reach that point. Okay? So how do I define this state function? I pick up a reference point, let's call it 0, and I decide that S of 0 is equal to 0. Okay? And then I say, well, okay, so then, given this reference point, let's take an integral along a reversible transformation going from 0 to any point x in parameter space of dq over t. And this is going to define my S of x, which is a state function. And what is the path with which I go from 0 to x? It doesn't matter. It doesn't matter as long as it is reversible. Because if it's not reversible, then you cannot even define this function. Okay? So please, when I ask you to calculate the change of entropy of something, so this function is called entropy. Okay? In thermodynamics, entropy. So when you're asked to compute a change of entropy, what you do is you pick up the initial state, you pick up the final state, you look at what they are, and then, independently on the cycle I'm giving, the transformation, free expansion, this and that, you connect these two guys by a reversible transformation and compute this integral along a reversible transformation. Because if it's not reversible, it doesn't make any sense. Okay? Clear? So it's a state function, pick an initial point, pick a final point, connect them by a reversible transformation, you choose it. I mean, if I give you 2 points which are at the same temperature, typically you choose an isotherm, right? But you might be, crazy and choose something else, or, an adiabath, an isotherm, an isocore, an isobar, and then get to the same point. It doesn't matter, you will get the same result. Okay? Good, this is called entropy. Now, in order to select the entropy, I have to define a reference point. Okay? And the reference point is completely arbitrary in thermodynamics. So, therefore, there is something that is called the third principle of thermodynamics. Principle of thermodynamics that says that if you take a system at 0 temperature, it has 0 entropy. Okay? It's not, on the basis of thermodynamics, I cannot explain this principle. On the basis of quantum mechanics, I can easily explain it. On the basis, look, imagine that, you know quantum mechanics, right? Some of it. So imagine that you have a state that is a system that has 3 states, right? Like a light, a traffic light. So we have a quantum traffic light, quantum mechanical traffic light. Red has some energy, high energy. Yellow has some low energy, the minimum energy, and green is in between. Okay? So we have the quantum traffic light is like this. Well, it should be the other way around, hopefully. So, green and yellow in between. So let's say that green has the lowest energy, just for simplicity. Great. So now, if I am at high temperature, my system is excited, is moving, it has all possible energies. So these 3 states have different energies. So let's say I have an energy E red, E yellow, E green. And they are different. So if I'm at high temperatures and I have some small energy differences, the system is not able to resolve those energy differences, and therefore has equal probability to be in one of these 3 states, which is exactly what is going to happen if I move my quantum car in the quantum traffic in the quantum city of Trieste, and I end up finding with some probability yellow, green, or red. But if you go to 0 temperature, which is exactly what happens overnight in Trieste, then only one of these states survives, the one of minimum energy, right? Which in this example is green, in the real Trieste is yellow, okay? And when you have one state, you know from information theory that the entropy is equal to 0, right? Because you always find that, so there is no information in that state. So it's the same thing in quantum mechanics, and that is why this third principle of thermodynamics is valid. It's based on this reasoning, okay? It's based on a very, very simple reasoning. And then go and read the books and find all kinds of complications, but life is simple in this case. All right, so typically then what you have to do in order, if you want to compute according to the third principle of thermodynamics, the state, you find the state at 0 temperature, and then you get to the point you want to get, and you compute the change of entropy, and that is your entropy function. Now, what is your entropy function useful for? We will see it next time. It's essentially useful to define thermodynamic potentials, and thermodynamic potentials are those objects whose minima, or maxima, depending on how you define them, tell you what are the equilibrium states you find your system in. For example, there is a thermodynamic potential called the free energy, the Helmholtz free energy, which describes a system in which you fix temperature and volume. and the maximum of, or the minimum of the elements free energy represent the equilibrium states at a given temperature and volume. Okay? So when I tell you then in statistical mechanics, what is the equilibrium state you are in today? You compute the elements free energy, find the minimum, and that's it. So it's something very, very practical. In order to define these two potentials, you have to use this object, the entropy. Okay, so that's what we will do next time, on Wednesday. All right, sorry for the mess in the calculation.
And that is the easiest problem on the exam.
I will try to simplify.
It's the arithmetic that makes
It's the fact that I'm talking, I'm hungry, and we will start the exam early in the morning. I will bring food and coffee, okay?